Good afternoon, learners. On behalf of IGNOU and on my personal behalf, I welcome you to the community of the students that belongs to IGNOU. It is our first video conferencing session for this batch, and as you know, first I would like to tell you what is the modus operandi in this university for teaching learning process. In IGNOU, we are having print material and non-print media. Print material we are having in the form of booklets that we generally call as blocks, and in general terms we call it as self-instructional print material. Print material because it is in the printed form, book form, and self-instructional because we try to prepare these books, to write these books in the form such that the clarity should be there, and when you go through those books or these booklets, it appears to you that it is the teacher who is talking to you through these books, and you should be able to read and understand through self-study. So that way we call them self-instructional. So this is one of the media, self-instructional print material, and in this self-instructional print material, here in this particular program, Advanced Certificate in Power Distribution Management, we are having 13 blocks, 13 booklets for the total 3 courses. There are 3 courses, BE001, that is Power Distribution Sector, in which we will be introducing you with the power distribution scenario, that what is all about in this power distribution sector. Second course is BE002, which is Energy Management and IT Applications, in which we will discuss about the energy management and application of information and technology in this energy management in various operations of this power distribution sector. Third course, which is BE003, this is Management of Power Distribution, in which overall managerial aspects that are being used in the power distribution sector, that we will discuss in this course. So there are 3 courses in all. In these 3 courses we are having 13 blocks, 13 booklets that we call as blocks, and in course 1 we are having 4 booklets or 4 blocks. In course 2, BE002, we are having again 4 blocks, and in BE003 we are having 5 blocks. In this, out of these 13 blocks, we have dispatched you 8 blocks in the first dispatch, and as I am getting reports from various corners, some of the students have received this material and some are yet to receive this material. We plan to send this material by speed post, and where this speed post facility is not there, at those locations it is being sent, or it has been sent by registered book parcel. So for the students who are living in areas where speed post service is not available, for them it may reach after 7 days, means by the end of the next week. But for the learners who are living in areas where the speed post facility is there, I have got reports that they have received some have received yesterday, some have received today. So, or it may take 1 or 2 days to receive to reach this material to all the learners. But for the learners who are living not in that area which is where the speed post facility or service is there, for them it may take the end of the next week. As far as today's video conference lecture is concerned, we will be focusing on the course 1 first. And the course 1, as you know, it is power distribution sector. In this course 1 also, we have picked up the first block to discuss today here, which is sectoral overview and the enabling framework. This particular block is having 3 units. Here today we will try to cover up the first 2 units. Unit 1 is power sector in the country, in which the overall scenario will be discussed, and second is acts and policies, in which we will be discussing the salient features of the acts and policies related to the electricity. So with this background, first I would like to introduce myself as well as with our experts. I am Dr. Munish Kumar Bharadwaj, faculty at School of Engineering and Technology, and at present I am also working as coordinator of this program, Advanced Certificate in Power Distribution Management. With me I have to my left Mrs. Anjali Chandra. She is Director, Central Electricity Authority. And to next I have Mr. V.S. Verma. He is Member Planning, Central Electricity Authority. These 2 experts are having very rich experience with them in this power distribution sector, and certainly I have full faith that you will be benefited by the discussions, by the lectures given by these today. So first I would like to invite Mr. V.S. Verma to please discuss about the power sector in the country. Mr. Verma.
Good evening, learners, the IGNOU students. I will take you through the power sector in the country, acts and policies, starting since independence. You will get the overview of the power sector, how we are going about it, how it has been developing, what kind of technologies we are adopting, and what is the scenario, and give you a philosophical touch also, how actually the power is generated and what the share of the various sources of power generation in the country. The historical background would also be explained to you. The evolution of the power sector since independence, how we have evolved. The power development in India started with number of small stations owned by the private industries, local bodies and the government establishments. Everyone was participating. It was kind of unorganized way of developing power. The first thermal power project of 1 megawatt capacity was set up by the Calcutta Electric Supply Corporation in 1899 in Calcutta in West Bengal. This is how the first thermal power station started in the country. Similarly, the first hydel project at Sivamudram, commissioned in 1902 to harness the potential of the Kaveri River with an initial installation of the 4 megawatt to provide electricity to Kolar gold fields. The transmission line associated with this project was 150 km long, the longest for that voltage. The voltage was 78 kV in the world then. The Tata Power Company, a private utility, built its first large power station of 50 megawatt at Kopali in 1914. This is how the development in the power sector started. You will be surprised to know that the total installed generation capacity in the country at the time of independence was only 1,362 megawatt. Imagine with the present installed capacity exceeding 1,35,000 megawatt, the installed capacity at the time of independence was only 1,362 megawatt. The share of hydro was 508 megawatt. coal and lignite. Lignite is also a type of coal, but it is called a young coal. It has not set itself, and it is mined at a very immature stage when it has actually not converted itself into the full coal. The 756 megawatt was being generated by coal and lignite together. The diesel engines accounted for only 98 megawatt of power at that point of time. And similarly, the per capita consumption was 16.3 kilowatt hour, means 16.3 units of electricity per person per annum was the consumption at the time of independence, and this number has grown to 665 today, 665 units per person. That means one must realize and appreciate what is per capita consumption. Per capita consumption does not mean the consumption of electricity by one person in the household, but this is the total electricity consumption in the country, and divided by the number of population in the country. So that is the share of a one person in the electricity consumption. That would mean its domestic consumption, the industrial consumption, the street lighting, the agriculture, for example, the commercial installations, all together. And the gross electricity generation in the country was 4,773 gigawatt hour, means million units. Gigawatt hour is million units. Unit is kilowatt hour. 1 kilowatt hour of electricity is known as 1 unit. Means if 1 kilowatt means 1000 watt is consumed for 1 hour, it amounts to 1 unit electricity consumption. And the maximum unit size in the country at that point of time was 15 megawatt only. Besides these, a large number of small diesel, thermal and hydro plants also came up in the towns of princely states, because India was ruled by the princes, by the kings at that time. And then from 15 megawatt, how the unit size increased actually. So since till the time 1980, the unit sizes of various thermal generators in the country, thermal was predominant in the country. It was 30 megawatt, the largest was 110 megawatt or 130 megawatt unit size. And the operational age of these units was 1 to 55 years. It means the 55 years old unit was also operating in 1980. The first 210 megawatt, this was a major change of technology. Till the units of 30 megawatt and 110 megawatt or 130 megawatt, the units were called subcritical and non-reheat units. When we generate electricity from the steam power plant, from a coal-fired power plant, the main we will explain in detail the procedure, the process, the technology for generation of this. But the coal is burned in the boiler, and then this heat is converting the water into steam. The steam goes to the steam turbines, and then it rotates the rotor. This rotational movement of this machine is converted into electricity through the generator. So when the steam, it is I hope you would read some other materials along with because everything it may be difficult for you to grasp, because they are highly technical in nature. So at the end of the lecture, I would suggest which are other books, technical books you must read to clarify some of the concepts. Like I am using non-reheat units, the subcritical units. These are thermodynamical terminology. If one needs to know, I would definitely explain what is non-reheat and what is subcritical units. But then at 210 megawatt unit was the first reheat type of unit. When we go for reheat type of unit, at the moment you can take this reheat word as one technical word which is used for reheating the steam. When steam goes and expands into the turbine for generation of the electricity, it comes out in a different state of thermodynamic state. It is called a wet steam. It has moisture contents in this, and degrees of superheat is less, and therefore this steam is sent back to the boiler for reheating, and that is how it is called reheat. In this process, the efficiency of the machine increases, efficiency of generation increases. So in 1977, first 210 megawatt unit, which was a reheat unit, was adopted with a higher efficiency. So it means the country went into a higher efficiency of generation. Now these units are upgraded from the point of view of efficiency only to 250 megawatt. It has so many other features have been incorporated which gives us a better efficiency. We went into increasing the unit size in steps. Why do we increase in the steps? There are many constraints. Efficiency is one. The manufacturing constraints is another one. You know, the steam is at very high pressure. For example, in 210 megawatt machines, the steam exists at 150 atmospheres. You can imagine 150 atmospheres and at a temperature of 540 degrees centigrade. It's a very high pressure and very high temperature. Once you compress the steam into such a very high parameters of pressure and temperature, its volume goes down, its specific volume goes down, and therefore when it enters the machine for expansion, the turbine blades size becomes very small. This becomes a constraint. This becomes a constraint of manufacture, and therefore with these parameters and with this machine rating 210 megawatt, perhaps we cannot increase the size of the blades. We cannot increase the pressures and temperature also, and therefore the limit of the unit size 210 megawatt was in 1977, and we continued with this size, with this efficiency till the first unit of 500 megawatt unit was commissioned in 1984 in Trombay, near to Bombay. The Tata Electric Company commissioned this plant. This was the first plant with a still higher efficiency. We adopted the temperature, the pressure range of 170. We went from 130, it was the pressure in the 100 megawatt units, which went to 150, and then we came to 170 pressure. We went on increasing the pressure so that we could extract more energy from the fuel at a high efficiency angle. So first 500 megawatt unit was commissioned in 1984. Since 1984 till today, we have been living with the 500 megawatt units, 200 megawatt units and 250 megawatt units, and the efficiency level almost remaining the same. And very recently, around the world outside India, the supercritical units of larger unit sizes, 660 megawatt, 800 megawatt, 700 megawatt, they had developed. The development of these units had actually taken place, but we did not venture into adoption of these unit size till very recently, since they need training of manpower, they need a higher standard of the water chemistry, and the erosion problems in the boiler. They are some of the very severe problems once you deal with high temperatures and high pressures in the machine. But then we went in slowly. Slowly we wanted to adopt this technology in our units, and the first unit having something similar feature like supercritical units were adopted in the 500 megawatt sets at Talcher of NTPC. NTPC has got a plant at Talcher in Orissa with the 500 megawatt units. We adopted once-through boilers. Once-through boilers means that the water enters and comes out as a steam. There is no intermediate boiler drum in these machines, but this feature is similar to a supercritical unit. So we thought that if we are successful in generating power with the once-through subcritical technology in our boilers, then perhaps we can smoothly have a transition to the supercritical units. The experience showed that it was a very successful attempt. The operators were trained. They did not find any difficulty in operating these units, and the water chemistry also we could meet from the indigenous water chemistry suppliers, for example, and therefore we decided that this is the time now when we could adopt the larger unit sizes in the country with supercritical technology. So about 5 years ago, about 6 years ago, I would say, we took a decision that we must follow the adoption of supercritical technology in the country. It takes time to adopt a technology. It takes about 6 years. to assimilate that technology, to manufacture that technology, to understand the intricacies of that technology, and therefore about 6 years ago we took a decision to adopt the supercritical technologies, and now the first supercritical technology unit is about to be commissioned in the country. This would be a 660 megawatt unit, and again NTPC would be the owner of these projects at SIPAT. This would be commissioned in March 2008. The first 800 megawatt unit, now we adopted, we want to adopt, but since we have to go in a very smooth manner, in a slow manner, so that the assimilation of technology is there, 800 megawatt unit is now conceived and is now planned in our 11th 5-year plan. 11th 5-year plan has already started, and it is coming to an end in the year 11-12, and this would come at Krishnapatnam plant of the Andhra Pradesh, and this is likely to be commissioned by 2011-12. These units are the most optimum size of supercritical units in the country. Once we say most optimal means from the angle of efficiency and from the cost considerations. 660 megawatt unit was not the optimal size of units, but then we thought that to start with this technology, it is a good size, knowing fully well that this is not the most optimum, but we ventured into a 660 megawatt unit, which now we are slowly we are changing to 800 megawatt unit size. The maximum capacity thermal in the country today is coming from 210 megawatt machines, 250 megawatt machines, 500 megawatt machines, and then 660 and the 800 megawatt units would be the next in the series. And why we are adopting these units is that there is a natural urge to save the fuel for power generation in the country, as well as there is an international pressure building up due to the environmental considerations, Kyoto Protocol, that we must adopt high efficiency and we must save generation of carbon dioxide in the atmosphere, which is a greenhouse gas. From these considerations, we have an internal understanding, we are very conscious about it, and we are following the higher and higher unit sizes, giving us higher and higher efficiency. Now this table which you see, it briefly summarizes with years what kind of unit sizes were there in the country, how we went along with the steam parameters, and how the unit heat rate. Unit heat rate, you can see the units of the unit heat rate, kilocalorie per kilowatt hour. It means for generation of 1 unit of electricity, how much heat you need from the fuel. This heat must come from the fuel. If you look at the number on the third column, which says that 1960 to 1970, 30, 50 and 62.5 megawatt were the unit sizes in the country. The parameters are indicated as 850 PSIG 900 Fahrenheit and 90 at 535 degrees centigrade, 1250 PSIG and 950 degree Fahrenheit. I am using in my presentation the PSIG and Fahrenheit as well as the atmospheric pressure and centigrade, because these were the standard parameters used at that point of time. If we look at 30 megawatt machine from the manufacturer, that was the rating at that point of time, 850 PSIG. One can convert this into the kilogram per centimeter square pressure by dividing by 14.7. So you would get the, similarly Fahrenheit can be converted to centigrade to have the idea. Those who are not familiar with these British units, one can do a conversion and find out. So on the unit heat rate column, you find 3529, 3386, 3206. It means for generating 1 unit of electricity, you need to spend something like 3500 units of heat, kilocalories. So much heat is given from 1 kg of coal. It means 1 kilogram of coal will give you so much of heat and will give you 1 unit of electricity. This is the kind of appreciation.
This heat varies with the quality of the coal?
This heat varies with the quality of coal, and the coal in the country is mined from several coal mines. These are located in the eastern region, and some are in the northeastern region, some of the northern region. and the calorific value of the coal of course depends on from which mine we are receiving, and it varies from 2500 kilocalories per kg to around 5000 kilocalories per kg. But the coal mines, the better grade of coal which has higher heat value, it goes into some other sectors like aluminium, it goes to the steel industry, for example, and the power sector is given the low quality coal, because we are able to burn this into the boilers, and therefore we receive coal around 3500 to 4500 kilocal per kg, and therefore to give you a broad idea, for generation of 1 unit of electricity, almost 1 kilogram of coal is burned. I mean, that is the, and then this efficiency in terms of percentage is something like 24%, 25%, 26%. That is the level of efficiency. What does it mean? It means that the 1 unit of electricity, if we burn 3500 kilocalories or 1 kg of coal, only 30% of this is converted into electricity. 70% is a waste. The thermodynamic cycle is such that there is a limitation, and we are unable to convert more than 30% of this energy into electricity. It goes and waste, and that is the area of research and development which has been followed over the period of time. Now look at the next row, 1970 to 1980, when we had 100 megawatt, 110 megawatt, or up to 210 megawatt. In 1980 was followed. The parameters of steam is also changing. We went on adopting higher parameters. From the 90 kg pressure, 1 ATA means atmospheric absolute. This is the meaning of ATA, and 535 degrees centigrade is the temperature, and you could see that wherever it is written 535 oblique 535, it means the main steam temperature is 535, and then this steam is sent for reheating. The steam temperature is also 535 centigrade. So this is a high efficiency cycle, and you see the heat rate number comes to 3099 kilocalories per unit, and which amounts to around 27.7% efficiency. So once we adopt from 90 kg pressure to 130 kg pressure, the efficiency has increased from 26.5 to 27.7%. Now still the innovations went on taking place over the units, 120 megawatt unit, 200 megawatt unit, 210 megawatt unit, and you could see the efficiency continuously rising from 26.5 to 27.7 and stabilized at 29.2. Efficiency of a system of steam generation mainly depends on the pressure and temperature you adopt. This is one. I mean, thermodynamically, ideally, this will depend only on the parameters as well as the sink. You know, the system of generation means that some heat is to be rejected to the atmosphere. It depends on the atmospheric temperature, the temperature of cooling water which exists at particular site. This cooling water is used for cooling in the condenser where the steam condenses, and that is the temperature of the heat sink, and therefore these two values, at the temperature of heat addition and temperature of rejection, are the boundary conditions for the limiting the efficiency of a steam cycle. But then it has something to do with the size of the machine as well. If the size of the machine goes on increasing, the blade heights of the machine, I will show you the cross section of the machine, how does it look like, and then you can appreciate the blade height is more, you can machine it better, you can give it a better curvature required, and smooth finish can also be given, and therefore the efficiency, marginally efficiency also depends on if the unit size increases. Now 1980 to 1990, we had 500 megawatt units in the country, and you can see that the pressure increased to 170 kg per centimeter square absolute, and 535 and 535. Now one can question that you went on increasing the unit size but did not exceed the temperatures from beyond 535 by 535 centigrade temperature. Now once we adopt a high temperature, this temperature is very high, and high temperature would mean metallurgy. Now there are metallurgical considerations that we could not adopt higher temperatures because if you adopt high temperature, the stress values are more. You have to select materials to sustain that over a period of time, over the life cycle. Life cycle is 25 to 30 years a power station exists, and with the proper maintenance you can increase the life to even 40 years, 45 to 50 years. In the beginning I told you that at the time of independence and at the time of 1980, in the year 1980, even 55 years old machines were existing in the country, and therefore if one keeps them running with the proper maintenance, one can definitely increase the life of the machine. So I was explaining that the temperatures have something to do with the metallurgy. The pressure is also something to do with the metallurgy, because pressure and temperature combined can become very stressful for a pipe which is carrying the hot steam in that.
So are the efficiencies higher in other countries of the world?
The other countries of the world, if we compare the contemporary machines,
Yeah.
the efficiencies are almost the same. That would mean, although these countries are claiming, or they would give you a higher number, but then when we report an efficiency, it has several parameters. The parameters would include the ambient temperature, the temperature of the cooling water existing there, the calorific value of the coal which they burn in them, and what is the basis of reporting. There is a gross calorific value, there is a net calorific value. Coal is the same, but if we say that the efficiency is based on the net calorific value, perhaps the number would turn out to be higher by 1 or 2%. And similarly, if in the other countries, especially the developed countries, the cooling water temperatures are existing which are lower, they are cold climate, and therefore efficiency naturally goes higher, because the sink temperature goes down. If the sink temperature goes down, the efficiency increases. If the sink temperature goes up, I think
so it's not by virtue of the design of the machine, but by virtue of the climate that...
the design of the machine sets the characteristics of the machine. Now this same machine, which if we just put in India, will give you a number, say 30% efficiency. The same machine, if it is taken to Germany, under the different boundary conditions, it appears to be slightly more efficient. Therefore, the numbers when you compare would need to be converted into the proper boundary conditions of pressure, temperature, ambient conditions, the coal quality, and there are a whole lot of things are there. Now I must come to the technological developments in the unit size. Now proposed is 660 megawatt units at Sipat and Bar. These are two locations in the country, where the steam parameters you can see we have increased to 240 kg per centimeter square, and the temperature is increased to 535 degrees centigrade and 565 degrees centigrade. Now you can again, someone can say that why did you adopt a higher temperature on the reheat system which is 565, why not 565 in the main steam as well? The efficiency could have increased. Yes, theoretically speaking, the efficiency could increase if we have a higher temperature, but then you see the main steam pressure is high, the reheat pressure is low. So combined together, if the pressure is low, we can go for higher temperature to keep the stress values the same. If the pressure is high, we will have to keep the temperature low so that the stress values are same as per the metallurgical considerations of that material. And the heat rate number is now 2400 kcal per kg. So we need, this is the heat rate 2400 kcal per kilowatt hour. This is wrongly printed as kg. So it means for unit generation of one unit, instead of 3500 kilocalories, you need only 2400 calories. That would mean that the coal consumption will be now proportionately less, and these machines will give you efficiency, higher efficiency between 1 and 2%. One has to do a lot of hard work and effort in increasing the efficiency even by 0.1% in the thermal power plants. The equipment is higher, equipment is expensive, the materials are costly, and that is how but we want to save every bit of calorie burnt in the boiler so that it could be converted. 800 megawatt supercritical units are still using higher parameters, 565 and 592 degrees centigrade, and its heat rate you can see from 2400 it has come down to 2325 kilocalorie per kg. I would suggest the learners, the students, if you get a doubt, you could definitely raise a question so that you clarify your doubt. It should not be remaining in your mind, and so that otherwise you will not be able to appreciate what are we saying. Now here you can see the unit sizes of the thermal capacity in the 11th plan and 12th plan. Now we have our 11th plan, these 5 years, which will come to an end in the year 11-12. The 12th plan would be next 5 years, which come to an end in 16 and 17. You can have an appreciation that 600 and 800 megawatt units in 11th plan are 14, 500 megawatt units are 58, 300, 200 and 210 megawatt are 59. Similarly, the smaller unit size numbers you could see 8, 139, and then so total megawatt which would come from the coal-fired power plants in 11th plan is 54,000 megawatt.
This is additional.
This is additional.
Additional in the 11th 5-year plan.
This is additional to what we have today. Today the installed capacity is 1,35,000 megawatt. So in addition to this, we are planning to add, you can see 54,000 megawatt coal, gas is 13 numbers module, and total megawatt from the gas is 4,000 megawatt. The total thermal from the gas and the coal firing is 58,000 megawatt. This is a very huge capacity we are planning to add in the 11th plan. The total target of capacity addition in the 11th plan is 78,577 megawatt. Out of that, 58,597 megawatt is coming from the coal and gas.
Considering the coal reserves in the country, there is a distinct shift from thermal to hydro. So could you explain that? We are trying to move from thermal to hydro. The thermal hydro mix has changed slightly in the 11th plan, which was higher in the 10th plan. Thermal was more than the hydro. Now we are moving towards hydro.
Okay, I think you raised a very good question. Firstly, that the coal reserves in the country today are exceeding 200 billion tons. 200 billion tons. All of them are not economically mineable reserve, and 70% of this would be economically mineable. But the reserves exist. They can be mined in one way or the another way. They can be converted to gas. The coal can be liquefied. There are so many options are available. And the coal consumption today in the country from the thermal power plants is about 300 million tons. 300 million tons is the consumption, and 200 billion tons is the coal reserve. Therefore, coal reserve would last long in the country. This is number one aspect. And second thing you said about hydro. Coming back to this, the coal consumption at the end of the 11th plan is increasing. We expect this to increase from 300 million tons to 550 million tons.
Per year?
Per year.
Per year. This will be the consumption per year.
Per year, 550 million tons, and we consume about 300 million tons per year today. And this is how the rate of the coal consumption is going high. You said hydro. The policy of increasing the hydro is from two considerations. One is the environmental angle. Hydro is a benign source and is a renewable source of energy. And secondly is the mix of hydro and thermal is required to meet the load pattern. There is a load pattern. There is a peak power, there is a off-peak power. The thermal plants cannot be subjected to wider load variations.
That means they cannot be shut down very fast and started very fast.
They cannot be shut down very fast, and they can be shut down in emergency fast, but they cannot be restarted
Fast.
So therefore, suppose the demand of the load goes down to below 60% of generation today, or at one point of time. A thermal power plant, coal-fired, will not be able to reduce the generation below 70% without taking certain exceptional steps like firing of oil or gas, additional coal, additional fuel, which is very expensive. It becomes uneconomical, and therefore the generator would not like to generate lower than 70% generation. If we suppose by any chance you force him to generate, next time he will prefer to keep his unit shut down, because it is very uneconomical for him to raise the generation from below 60% to the full load generation. This is one limitation. Therefore, at such occasions, the hydropower comes very handy. Hydropower, quickly you can load the machine to full load, and you can as well. Yes, please.
Yes, Lucknow, you please ask your question.
Sir, I am Govind.
Yes, welcome.
Sir, as per record, India and Asia operates our power plants at 50 hertz.
Yes.
But Japan uses both 50 and 60 hertz. Please explain me the frequency, the disturbance in frequency, or various types of frequencies may increases our efficiency of power plants.
Let me explain. The frequency of operation in a thermal power plant has something to do with the say rotation. Once you come back to the power generating unit, the 50 hertz of frequency would mean 3000 RPM of a thermal machine.
Rotation per minute.
Rotational 3000 revolutions per minute, and 60 hertz would mean Anjali, how much? 60 hertz would mean accordingly. I think you can
work it out.
You can work it out. 50 hertz and 60 hertz. There is a formula 12 F by P.
Yeah.
You can work out from the pole
Number
of the
of
machine.
poles, actually it requires the number of poles.
And but then 50 hertz or 60 hertz has nothing to do with the efficiency of generation. It is one system adopted in the country, and Japan, if it has 60 and 50, there are many countries who are having different frequencies in different parts of the country. The reason is not that they could not generate at 50 hertz, but at some point of time there must have been compulsions of importing machines of a particular design to operate in that area. The grids are interconnection is very important. If the grids are to be interconnected, then the whole grid has to operate at one frequency. Now, India also had 5 regions which were not interconnected, north, west, east and northeast, south as well. But all our grids were operating at the operation frequency of our grid were designed as 50 hertz, although there were variations.
So what I think he means to say is that is the efficiency affected by the frequency, which I feel it is not affected by the frequency. Efficiency is more related with the steam parameters and the coal.
Efficiency has nothing to do with the frequency, yes. And you could have different frequency and the same efficiency.
Yes.
So USA has 60 hertz, and we are following 50 hertz, and Germany is following 50 hertz, like that.
Exactly.
So at this stage, we would like to close this session, and we will continue these discussions in the next session at 5:30. So we will meet at 5:30 and continue these discussions. So our learners can ask their questions and queries in the next session also. Thank you.
Thank you.